Okay, we are going to discuss continuity. Specifically here, we're going to talk about whether or not a function is continuous at some x value x equals a. We're going to do a definition here in just a moment. I'll have you write that down. But first what I want to do is I want to take a look at a couple graphs, a couple illustrations, and see if we can't sort of discover what this means for a function to be continuous at x equals a. Okay, so I'd like you to draw the following graphs. For each one here, I'm going to mark this x equals a, and for this function, I'm going to draw it. I'm going to put a hole at x equals a, draw it like that. Okay, and that's going to be f of x. Now let's draw a couple other ones here. Similar concept. Maybe change the behavior a little bit, and we'll have a point up here. X equals a. This again is f of x. And in the last one, let's come over here, close the circle, open the circle, and that graph is f of x also. And I'm almost forgetting here, x equals a. Okay, so here's some three graphs we're going to look at, and maybe think along as I talk. Which one of these is continuous at x equals a, if any? So perhaps let's go through each one. What do you think? Number one. Is this function continuous at x equals a? Think about it. Number two, is this function continuous at x equals a? Think about it. And number three, is this function continuous at x equals a? Please notice that I am not asking the question, is this a continuous function? That did not come out of my mouth. I asked whether or not the functions were continuous at x equals a. Before we answer those questions, let's answer a new question. This question is, does the function have a limit as x approaches a? Different question altogether, not continuous at x equals a, but does it have a limit at x equals a? For the first one, does this have a limit? And the answer is yes. That was the point of the previous lesson. The limit here we will call L. It's a real number L. For the second one, does this have a limit? We know the answer to that question is yes. As x approaches a, the function gets closer and closer to the real number L. And finally, this last one here does not have a limit. So we'll say the limit does not exist. Here we'll say the limit equals L, and here we will say the limit equals L. Pretty straightforward. Next, I want to ask whether or not the function even has a value at x equals a. So for this one, f of a, well, what is f of a? Nothing. There's a hole here. F of a does not exist. For the second one, does f of a exist? Yes. F of a exists, and in fact, it equals some other real number. Let's call this real number r. So f of a equals r. It exists. And in the third one, what is f of a? It actually does exist. Let's call this one L. Okay. Now, what would make these functions continuous or not at x equals a? Well, let's answer that question finally. All three of them fail to be continuous at x equals a. The first one is not continuous at x equals a, the second one is not continuous at x equals a, and the third one is not continuous at x equals a. So what needs to happen in order for it to be continuous at x equals a? Well, that's going to be the point of the definition. So we're going to write the definition down now, and hopefully we can piece it together here to make complete sense of it. So a function is, I'm going to underline this, continuous at x equals a. It doesn't say a function is continuous if and only if. So a function f is continuous at x equals a if and only if the limit as x approaches a of f of x is equal to f of a. So you see here there are two parts. We need to find the limit, and that was the point of lesson 1. And then you need to come over and find the value of the function f at a. And then thirdly, you would compare them. And if those two are equal, well then the function is continuous at x equals a. The one that's closest, I guess, to being continuous would be number 2, but it's not. What we would need to happen is we need to erase this point and then plug in the hole. Now, that would come down here, and then this would be L, and this would be L, and then it would be continuous at x equals a. Okay, I'd like to take a look at a fourth one here. So let's draw our x equals a. This time the function is going to come up, approach it asymptotically, like this, and then same from the right hand side. So this is f of x. Now that's really sloppy. Make my arrow. Okay, maybe I'll even give this a dotted for the asymptote. Okay, so be careful here. The limit as x approaches a of f of x, well, we would say infinity, but if you recall, infinity means does not exist. And then if we would try to evaluate f at a, that also does not exist. It is not the case here. What I'm about to write is not true. They're both have this not existing quality. That doesn't mean this. It doesn't mean that does not exist equals does not exist. That is not a true statement. If something doesn't exist, it can't equal something else. So, in the case that you have an asymptote, the function is not continuous at x equals a. We are now going to look at a couple examples. Each of these examples is going to be a proof. F of x equals, we're going to make this a piecewise function. Let's go 5 minus 2x, provided that x is greater than or equal to 1, and the other condition, x squared plus 1. Sorry, that's the expression for the condition x is less than 1. And the directions are to prove whether or not f is or is not continuous at x equals 1. I'm going to write this definition that we have. Probably should have written it at the top of the page, but I want to be reminded that it is continuous if the limit as x approaches a of some function f of x is equal to f of a. I wish I wrote that at the top, but you can do it. So we are now ready to do a proof. I like to partition this into 3 steps, I, double I, and triple I. I'm going to encourage you to do the same. You have freedom to deviate from that 3-step proof, provided that you have all the pieces. And I find that people who do the 3 steps do not end up making an error, and I will point that out as we go through. Okay, in this particular problem, so here we have f of x, and this is always generically x equals a, x equals a. So in this first problem, our a value is 1. That's the point in question, whether or not it's continuous at x equals 1. So the first thing I want to do, and on the other page, I put a blue box around this. It ends up being the first thing I do. I want to evaluate the function at a, and in this case, I want to evaluate the function at 1 to see if it even has a value. So f of 1, if I plug that in, now I'm going to plug it into the top because this is the condition x is greater than or equal to 1. And when I plug that in, it's going to be 5 minus 2 times 1, which comes out to be 3. Okay, so that's real easy. Step 2. Step 2 is always the step where we find the limit. So let's treat this like it was a homework problem or an example from last class. Step 2 is only about the limit as x approaches 1. Now we notice this is piecewise function, and the behavior to the right of 1 is different than the behavior to the left of 1. So if you recall, we need the 2 one-sided limit theorem. So we are going to need the limit as x approaches 1. Let's start with the right of f of x. Remember, we do that generically, followed by the behavior to the right. And the behavior to the right is going to be this 5 minus 2x. And to solve this, we use substitution, 3. So everything is looking pretty good. Next, I want to find the limit as x approaches 1 from the left of f of x. which is the limit as x approaches 1 from the left of the behavior x squared plus 1. I'm going to substitute that in, and we have the number 2. Okay, now embedded inside this step 2, the double I, we learn that since these are different from one another, it doesn't have a limit. So the conclusion made in step 2 is that the limit as x approaches 1 period of f of x does not exist. Now step 3, you must have this written somewhere on your paper. If you have it in step 3, that's great. We're going to write the definition, so the limit as x approaches 1 of f of x, and we're going to compare that to f of 1. Okay, so this from above was equal to 3, and this from above doesn't exist, so the minute you have one of the two features failing to exist, these cannot equal each other, and then we conclude finally that therefore f is not continuous at x equals 1. So let's pose a question here. Suppose that someone only put this step 2, then they accurately wrote this. Is that wrong? The answer to that question is no, they're not wrong. They didn't need step 1 because the minute either side of these fails to exist, then you're allowed to skip to the definition and say they're not equal. But I want to warn you, I still like all 3 steps because what happens is, let's say in step 2 that the limit was equal to 3, and in your mind you knew that f of 1 was equal to 3. You just knew it in your mind, but you didn't write it. Well, then you can't conclude this because I don't see anywhere on your paper that tells me what f of 1 is. Let's take a look at the next example. We're going to call the function here g of x, and g of x is also a piecewise function. Here it's going to be the absolute value of x minus 2 over x minus 2. But that's going to be provided that x is not equal to 2. At the bottom of this piece, I'm going to say that the function equals 0, and that's provided that x is equal to 2. And we're going to prove whether or not g is or is not continuous at x equals 2. So our a value, our point in question, is 2. And we're going to do the proof. But you know what? Before I do the proof, I want to rewrite this. So I have this absolute value, and it's kind of making things tricky. So I'm going to extend this piecewise function utilizing our definition of absolute value. And so this is when x is greater than 2. We have the opposite of x minus 2 over x minus 2, provided that x is less than 2. And then finally 0, provided that x equals 2. Let's simplify that. It's going to make our life a little easier. So the function g is equal to 1 when x is greater than 2. The function g is equal to negative 1 provided x is less than 2. And then the function is equal to 0 provided that x equals 2. I want to also warn you that the point of these questions isn't for you to say in your mind and blurt out, I know the answer, and then show no work. You better be able to do it. I mean, you should be able to look at this right away and determine whether or not it's continuous. That is not what I'm asking you to do. I'm asking you to articulate through a proof your understanding of continuity at x equals a. Okay, step 1, we want to determine g of 2. And g does have a value at 2. It equals 0. Step 2 is about the limit. Okay, now the behavior to the right of 2 is different than the behavior to the left of 2, so I need 2 one-sided limit theorem. And so the limit as x approaches 2 from the right of g of x equals the limit as x approaches 2 from the right. The behavior to the right is the number 1. And the limit of a constant is the constant. Let's come over here. The limit as x approaches 2 from the left of g of x equals the limit as x approaches 2 from the left of -1, which is -1. Looks like we're going to have a similar scenario here. The two limits are different. Don't skip and say right now, oh, therefore it's not continuous. Let's be methodical about it. In step 2, the thing that we have concluded in step 2 only is that the limit as x approaches 2 of g of x does not exist. Again, since we have this does not exist, we could have skipped step 1. Now I come to the bottom here, step 3, that's a comparison of the limit as x approaches 2 of g of x as compared to g of 2. These cannot be equal to each other because the limit didn't even exist. And then we make the grand conclusion based on this statement here that g is not continuous at x equals 2. Okay, last example of a proof. H of x is piecewise. We have a rational expression when x is not equal to -1, and then just the number 4 when x is equal to -1. Okay, here our a value is -1. Before we do anything further, though, let's take a look at this expression. I see that I can simplify this. I have a difference of 2 squares. Okay, and since I have that, it looks like the portion is actually just x minus 1. So this portion here is just that. So let's write h of x differently. Let's say that h of x is going to be x minus 1, provided that x is not equal to -1, and then the number 4 when x does equal -1. Okay, that's going to help us. So let's do our proof. Step 1. First thing, what is h at -1? And I come over, and h at -1 is 4. Great. Step 2 is about the limit. Now I want to point out here that you do not need the two one-sided limit theorem. The behavior to the left and to the right of -1 is this linear expression. So it's a line to the right and a line, the same line to the left of -1. So since the behavior is the same on both sides, I do not need the two one-sided limit theorem. I can go right for the limit. Step 2 is all about the limit. So the limit as x approaches -1 of h of x equals the limit as x is approaching -1, not equaling -1, but approaching. So that behavior as it approaches is this line. And then with some substitution, I see that that is -2. So this one is different from the other ones because both of these exist. That was 4, that was -2. And I think you see, though, they're not equal to each other. Notice I don't have a therefore statement. The statement stands alone. I've just said that the limit of h is equal to -2 as x approaches -1. I don't need to restate with a therefore. Okay, in step 3, though, I'm going to compare the limit as x approaches -1 of h of x and compare it to h of -1. I'm asking on the test, a quiz, any assessment that I must see this equation, and then you must evaluate whether or not it's true. Here, they are not equal, and we conclude that h is not continuous at x equals -1.